Good morning, everyone. I am Pratyusha Das from University of Southern California. Today, I'm going to talk about our paper on graph-based skeleton data compression. So this is the roadmap. I'll start with the motivation behind the work. Then I'll talk about graph Fourier transform, the spatiotemporal graph we have used in this paper, the proposed graph-based skeleton compression, which includes graph transformation, quantization, and encoding. Next, I'll talk about the results and then the conclusion. So, motivation. Skeleton data information extracted from video has significant importance in many areas like action understanding, monitoring or surveillance, telehealth, sports guidance, autopilot, mobile robots, human computer interfaces. Uh, Skeleton information can be extracted using devices like Microsoft Kinect, or we can directly use softwares like OpenPose, which can extract skeleton information directly from the videos. But then what is the need of compressing the skeleton data? The increased use of the skeleton data motivates the need of efficient compression methods. A system monitoring 5% generate around zero point 0.2 billion real values in an hour. So we can imagine how huge the data amount will be if some system is monitoring labors in a factory for a day. So this demands on transmission and storage capacity. So that's why we want efficient algorithms to compress the skeleton data. So I'm coming to graph Fourier transform now. Let's say we have a graph G which has a vertex set V and edge set E, and the adjacency matrix of that graph is represented by A. And the cardinality of this graph is n. That means there are n number of nodes. We construct the Laplacian matrix using this equation. You can see the I is the identity matrix n cross n, D is the degree matrix of the graph, and A, as I mentioned, is the adjacency matrix. Now, if we do the eigenvalue decomposition of this Laplacian matrix, this is the normalized symmetric Laplacian matrix. So if we do the eigenvalue decomposition of this Laplacian matrix, the eigenvectors are basically the graph Fourier basis, and the eigenvalues, corresponding eigenvalues, are the graph Fourier frequencies. So this lambda is the diagonal matrix which contains the graph frequencies. Now, how we design the spatiotemporal graph. So the spatial graph, which is the skeleton graph, is inspired by the human anatomy. It has, you can see, 25 number of nodes and 24 number of edges. We are compressing the data, skeleton data given by Kinect, which gives you 25 joints. That's why we are using this graph. If we are compressing the skeleton data from any other devices, we have to see that how many joints they are providing, and according to that, we can change our spatial skeleton graph. If I do the graph Fourier transform or graph Fourier analysis of the skeleton graph, we find the graph Fourier basis. So here I show you the spatial graph Fourier basis. Lambda represents the frequencies. I want to talk about the node color. The node colors represent the sign of the elements of each basis. Green means positive, red means negative, and blue means 0. So this is the first basis corresponding to the smallest frequency, which is 0. And you can see if we apply this transformation, basically it captures the average graph signal. The second one, which corresponds to the graph frequency lambda equals to 0.02, basically captures the variation of the graph signal present in the upper body and the lower body. The third basis, corresponding to the graph frequency 0.03, captures the variation in the left hand and the right hand. But as we increase the graph frequencies, let's talk about this frequency, which is lambda equals to 2, basically captures the variation of the consecutive joints. So thus we can say that these graph Fourier bases are interpretable, and according to our need, we can change our graph and capture the necessary information. Now, how do we design the graph, spatiotemporal graph? So spatiotemporal graph is nothing but the canonical product between the spatial skeleton graph and a line graph. The graph Fourier basis in this case also is a canonical product between the skeleton graph and the line graph basis, and it is a separable transform. So that means if we want to apply this spatiotemporal graph Fourier transform, we can first apply the spatial graph Fourier transform on the graph signal and then the temporal. Now I'll talk about the graph-based skeleton compression. This is the block diagram of our proposed method. Our skeleton data has a dimension of number of coordinate cross number of frames cross number of joints. First, we go to the transform domain. We apply the spatial graph Fourier transform and then the temporal graph Fourier transform. We quantize these transform coefficients. We both tried with uniform and non-uniform quantization. Then we apply a scanning. At the end, we do encoding. Here we are using the encoding similar to JPEG, and we get the bit stream. So this is the temporal graph Fourier transform. So if we do not apply the spatial graph Fourier transform and only apply the temporal graph Fourier transform, this is the energy in the transform domain. As you can see that all the energy is concentrated in the smallest temporal frequency, and these x-axis represents the joints. But if we apply both the spatial and temporal graph Fourier transform, so basically first we apply this transformation and then we apply the spatial transformation, we see that we get better energy compaction in the lowest frequency range. As you can see here, both in x coordinate, y coordinate, and z coordinate. In terms of quantization, we tried both with uniform and non-uniform quantization. As human motion has the energy of the human motion signal lies in the lowest frequency. So the highest frequency energies are the noise in the temporal domain. So that's why we tried with this kind of quantization, where we are trying to give more quantization in the higher frequency or higher temporal frequency. So as you can see, the quantization in this case is increasing as the temporal frequency is increasing. We also tried with another method, which is where we are increasing the temporal uh, quantization amount in a zigzag pattern or in diagonally. And we saw that if we increase the quantization amount according to the increase of the temporal frequency, it works much better. So these are the results. So when we apply the uniform quantization and we compare uh, the compression only using DCT and using graph based skeleton compression, we get better mean square error when using graph based skeleton compression while using the lower bit rate. But if we increase the bit rate at some point of time, it will be similar. So if our operating region is the lower bit rate, then obviously we would like to go with GSC. Usually in this case, the operating bitrate region is 1 bits per joint. So this is bits per joint. This is the signal reconstruction after using the non-uniform quantization technique. As you can see that if we use GSC can capture more detailed information, while DCT is only trying to keep the DC level of the signal. This is the RD curve for non-uniform quantization. Here we are comparing DCT, GSC non-uniform while using the GSC zigzag or the diagonal increment of the quantization amount, and the temporal increment of the quantization amount, and which I name as row major, GSC row major, because I am increasing the quantization amount row wise. So we see that GSC row major works best among these three. So this is the summary table. And if we compare the root mean square error, GSC with temporal increment in the temporal quantization amount works the best. And also we can achieve this much amount of RMSE with a very low bit rate. While we are comparing the performance of this compression data in terms of action recognition, we did not find much difference if we use the no compression signal and the compression with GSC. Even we can see little increment in this case while using the compressed signal. This is probably because the noise is reduced in this signal, because we are trying to cut off the higher frequency, or we are quantizing more the higher frequencies, and that's why we are achieving better results, or very like little better result in this case. So to conclude this work, we introduced a graph-based approach for mocap data compression. This is a separable spatiotemporal graph transformation that achieves good energy compaction for typical data. We can do fast implementation of this method by using fast graph Fourier transform, as these graphs are bipartite. So we can easily use or implement the fast graph Fourier transform, which will save time in this case as well. Thank you.